Hello everyone, we are Ariel and Oren, and today we'll present to you our project, Green Light is All You Need. In this project we researched the topic of reinforcement learning and implemented a deep reinforcement learning model for traffic light management. So we'll start with why do we even need this kind of a model? What are we trying to solve? Later we'll show you how we approach the problem and which solution we worked on. And finally we'll talk about the results we achieved. As technology advanced, today we have supercomputer chips that are a trillion more times capable than these old computers, but traffic appears to have stayed the same. So breaking down the issue during traffic rush hours, the intersection does not understand what is going on, and this creates traffic jams. On the other end, during off-peak hours, you can get stuck even though you are the only one waiting to cross.
First of all, we needed a traffic simulation. We found Sumo. Sumo allows to simulate all kinds of intersections with different traffic flows, and above all, it allows us to extract all of the necessary information needed for our model. We wanted to train our model on real-world scenarios, so we used light traffic scenario and a more busy traffic intersection, as you can see from the distribution graphs. Reinforcement learning is not a single training method, but as we can see, there are plenty of different ones. Within all of these options, we chose PPO, that stands for Proximal Policy Optimization. The reason we chose it is that we wanted a method that wasn't too complicated for us to implement from scratch, but also to give us decent results. So the way PPO works in general is that we have an environment, in our case a traffic simulation, out of which we extract a state that includes vehicle speed, position, waiting times, and more. This state goes into the actor, which is a DNN model. The actor calculates an optimal action. In this context, it's which lane gets the green light, and then it is put back into the environment, aka the simulation. After the action is performed in the environment, we calculate our reward, which is how good was the action. The reward is sent to the next model, the critic. The critic takes both the state and the reward and calculates the advantage, which is a value that represents how good the action was relative to the average action. The advantage is used to train both the actor and the critic models, and the cycle then continues.
So as we said, both the actor and the critic are deep neural networks. In our case, we chose a multi-layer perceptron with four fully connected layers for both of the models. The actor has a softmax layer at the output that gives us the probabilities from which the action is chosen. The critic gives us one value that is used to calculate the advantage. So the actor tries to maximize the advantage that it is given, and it does it by increasing the probability of actions that lead to higher advantages. When it becomes too confident, it gets punished by an entropy loss. Also, we try to explore random actions once in a while to try different policies. The critic goal is to give us a better advantage function. The advantage is an expected return relative to an average return from all actions, but this value is theoretical. Therefore, we estimate it with temporal difference, which is calculated by the critic or using the critic. Positive temporal difference means the action was better than the average, and negative one means the action was not so good.
The reward is decided depending on what sort of performance we hope to achieve. We tried several different ones. The first was average speed. As we can see, the average speed reward led us to a bad state. The model converged not as expected. Also, we tried accumulated waiting time and a mixed reward that was the weighted sum of both values just mentioned. These didn't lead us to convergence, but rather, as we can see from the graphs and video, a random action selection. So after training the model for 200 episodes, looking at the total waiting time and average speed per episode, we don't see a clear-cut improvement, nor for the light traffic, nor for the heavy traffic.
And although the results were not so promising, we compared the model to two other policies. The one is automatic lane changing every 30 seconds. The other one was lane changing by our judgment and the model. For light traffic scenario, we could see a big difference. The automatic policy did really bad. The model was decent and the human was the best. For heavy traffic, the difference between the model and the human was not so big. This is probably because switching randomly the traffic lights resulted fair traffic for all lanes. So after trying a lot of different ways to make our model work, we figured out that maybe this kind of problem needs a different approach. And it takes a few steps for the environment to get the reward. So maybe using a multi-step proximal policy optimization can handle this delay. Also, off-policy training and using memory to experience a replay after each episode could have helped improve the results.
Throughout the work on this project, we had to learn and research on different reinforcement learning methods and choose the one that seemed to fit the best. Also, integrating the simulation with the model was not easy and took a lot of work.
If we could extend this project one day, we would try a smarter reward function, maybe more complex intersections, more lanes, and different kind of vehicles, like trying prioritizing emergency vehicles. And most importantly, we had a lot of fun working on this project, and we learned a lot. Thank you.